Okay, this video will walk through the steps and some analysis for interpreting factors a um, after a factor analysis has been run. We want to be able to interpret and determine whether the proper number of factors have been returned and try to understand where to go from there. So this is the interpreting factors stage after we have determined how many factors we want to try to call and the method in which we want to perform our factor analysis. So once we run the analysis, the the data will be what we call rotated, or the solution is what we will call rotated. And so that we want to talk a little bit about that. Then we want to look at our data and interpret which factors and variables are meaningful. And then we want to be able to walk through this process to make sure that that our solution that we come up with is something that we'll be able to use. Once the factor analysis is begun, the software will extract a solution, and the factors that are returned will be what we call orthogonal, meaning that the assumption will be that they do not share variance, that the factors do not share variance with each other. And so that's the first thing that happens is within the software, an initial solution is provided, which breaks down the different variables, pairs together the variables that make sense, and again creates what we call orthogonal factors. The strongest factor that is returned first has the greatest eigenvalue, and there will be factor loadings that are provided for the initial solution as well. So those factor loadings then are kind of like, they're mostly interpreted to be like correlations that are shared, the shared correlation between the variables and themselves within the factor. Okay, so the stronger these are, the bigger these are, then the better is basically the interpretation that you want to think about. After this initial solution is returned, what we'll often want as a researcher is for something we call a factor rotation. And when the data is rotated, or when the factors are rotated, basically what's happening is the factors are adjusted to better account for variability across all of the solutions and across all of the factors that are returned. So there's a lot of theory, and there's a lot of resources, and there's a lot of information on different types of factor rotations, and we'll actually have a lot of options available to us, and they're basically broken down into two components, either orthogonal rotations or oblique rotations. So orthogonal or oblique rotations are the two most popular. Varimax, which is a term, it's a type of rotation. A Varimax rotation is probably the most commonly used orthogonal procedure. And then when we look at oblique rotations, then what is most often used, or very often used, is what's called a Promax rotation. So if you're doing this work, either a Varimax or a Promax rotation is used. As a standard practice, I generally use a Promax rotation because it returns what we call a pattern matrix, a factor pattern matrix, and I find that to be the most interpretable for my uses. The other thing that it does is it subsumes that the data, or that the factors that are returned, will not be, or will be correlated with each other to some extent. So in other words, we have factors that are returned, and in an orthogonal procedure, we kind of make this assumption that the factors are not correlated, but the reality of just the way things are, reality would suggest that most often than not, factors will be correlated at least some. So the oblique rotation allows for a more relaxed condition, I guess, that would permit permit correlated factors to exist. So that's why I generally use a Promax rotation. So oblique rotations are sometimes thought to be more meaningful than because they allow for factors that are mutually correlated. And so the challenge with that, or sometimes we have a bit of a challenge where sometimes the data returned in oblique rotation, or the solution returned, may be sensitive or more sensitive to specific features of your sample. So anyways, with that said, you've got a lot of options here in terms of being able to rotate your data to produce a solution. I, again, generally run with a Promax solution initially. And so when you're testing and playing around with factors, you may want to just try different. So now at this point, once we have the data rotated and we have solutions, a solution presented to us, it's now time to start looking at the factor loadings by variable and look at how each variable loads on each factor to determine the proper assignments that are going to happen here. So when we look at factor loadings, then we want to look at the size of the loading and how strong it is. Generally, with a final solution, we want factor loadings that are above a 6. I mean, that's something that we would want to have. But there may be statistical significance at anything above a 3. 0.3 on this, and these might be minimal, relatively important, and offer some practical significance. But again, I like to use the general rule of above 6 or above 7, somewhere in that range. Sometimes you may drop to above a 0.5. So you have significant relationships and loadings here, like coefficients, but again, you want ones that are going to be practically significant and high enough. So there are generally rules here. With the greater the sample size, like a lot of ways here, a lot of techniques, the larger the sample size will produce significance at lower factor loadings. So I may have a significant result that's returned with a factor loading of 0.3, but for all practical purposes, that's not significant for me. I need to have something that is going to be somewhere up in this range, 0.65, 0.6 or higher, 0.7 or higher, something that's up here. And even if I have a very large sample size, I still want to have these as loadings. So as an illustration, we can look at kind of some steps, I guess, that would be involved in examining the rotated solution and examining what we would do to retain factors and retain variables. So we want to look at the rotated pattern matrix. That's what I would recommend doing, and look at the loadings that are associated with that pattern matrix. We want to put in order, if we can, if your software will allow you to do this, we want to put in order the variables based on the size of the factor score. So we want the strongest factor scores to be reported first. As we look at each factor, we want to look at the first factor, and we want to consider the variables that load heavily on that factor, and we want to make a consideration as to whether we think that those factors or those variables should go together on the factor that we're looking at. Then we want to also look at the actual size of the loading and make sure that they're practically significant. So in other words, are they above 0.5, 0.6, 0.7? And that's a key thing to look at. Next, we want to go to our next factor, and we want to continue and repeat the process. We want to continue to look at the factor loadings and make sure the variables seem to make sense. The other thing that we want to look for as we begin to look at numerous other factors is we want to look at something called a cross-loading. In other words, sometimes we'll have variables that will load on two factors at the same time. So generally that's problematic, and we don't want to really have that happen. So we want to take a look at what we call cross loadings to make sure that we are not in violation of that. If we choose to drop a variable, then we need to drop a variable and then rerun the analysis and look at the results. Okay, so continuing to analyze the loadings, continue to look at the factors, making sure that they make sense, and then rerunning the analysis is the process that we basically will look at. So what I have here is an example of our HBAT data. So the HBAT data, and what we're going to do is pull variables 6 through 18 and basically look at this. So I've run the analysis for variables 6 through 18. I did a ProMax rotation, ProMax solution here. I have this initial table, so total variance explained table. This first column gives us our total variance by, and these would be by factors. So this is factor 1, 2, 3, 4, 5. We have a proposed factor for each variable or for the number of variables we have. Now the eigenvalue rule or the latent root rule is that for each component here, each potential factor that's greater than 1, we would call that as a factor. We would want there to be 5 factors. So if you're using the latent root rule to determine how many factors you'll have, then 5. 5 is what is here. It's greater. 5 factors are greater than 1. If we go to the scree plot rule, you look at the scree plot that is produced for these 13 variables, and again we have an eigenvalue for each one of the potential factors. We have 5, 1, 2, 3, 4, 5 here. This is the 5th one that are greater than 1. And the key here with the scree plot is that it's interpreted. What you want to do is you want to look for the point in which it levels out in terms of the data. So we have the data that kind of breaks here, and what you want to look at is the point in which it breaks. So here you could have a break here. Some would say maybe the break is here. If the break is here, then you have a 5 factor solution. If you break down below here, then you may have a 6 factor solution. So again, this is it's really where the break happens, and so you could consider this either a 5 or a 6, potentially a 6 factor solution. And the luxury that we have with software computing power is that we can run multiple attempts here, and just kind of by trial and error we can see what works best. Okay, so continuing on, if we do this and we run a 5 factor solution, then this is the pattern matrix that is returned. So again, as we look at the pattern matrix, we have the first factor. So this is the first factor here. This has the most variance explained, the eigenvalue with the strongest variance here. We have variable 18, 9, and 16, which seem to go together. And so that's delivery speed, complaint resolution, and order billing. And we have very high loadings. Again, these are all above 0.5 or 0.6. Now, down below here, we have some other ones. We have price flexibility and product line. Here's the challenge though. These also are going to cross-load onto other variables. Now, in this case, we're looking at some negatives and some positives. Don't be too concerned about that right now. What we're looking at is at the magnitude of the coefficient. So the magnitude of the coefficient is what we're looking at, and inside these boxes we have these would be the variables that would go with factor number 2. We have variables that'll go with factor number 3, and then 4, and then 5. Now, there are clearly some issues here. One, we have 2 variables that are cross-loaded. And then also we have some factors here that only have 2 or even 1 variable. So again, we don't want factors, generally speaking, we want to have factors that have more than 2 variables that support them. So factor 4 and factor 5 are questionable. However, it is possible to have 2, though it's not desirable. So what I would do, and what I've done here, is I would go ahead and consider dropping variable 17 and 11 because they're clearly cross-loading on 2 different factors, and that's going to be problematic when we do analysis later on. Okay, so I've rerun the data with those 2 factors eliminated. So those 2 variables eliminated, 11 and 17 have been dropped. Rerun the data, and now, interestingly enough, we have a 4-factor solution instead of 5. So there were 4 factors that had an eigenvalue greater than 1. And inside the boxes here are the loadings, the factor loadings that are associated with these different factors. And then we have this last one again, which is a little weird because it only has 2, and we have a new problem that we didn't have before. We have this x15, which is a variable that really doesn't load on any of the factors very strongly. This 0.3303 is the strongest, but for a factor loading, that's still too low. So the next step here now is to drop x15 and see what we come up with. And sure enough, we have a better fitting solution, a better solution overall. This is still a little bit of a problem for me personally. It means that, you know, we've got 2 things that really don't explain one underlying concept here. And actually, if we look at these items, product quality and product and competitive pricing. So my quality and my competitors' prices, what this suggests is that these are inversely related because we've got a negative and a positive here. So something weird is going on here. The interpretation of this as a factor is really hard to make, to be quite honest. We have technical support and warranty claims which go together. We have Salesforce, e-commerce, and advertising which seem to go together. And we have complaint resolution, so that's a service type of a thing, delivery speed, and then order and billing. So these are all sort of delivery service type issues. They go together. So these first 3 factors, we would name them. We would want to give them a name other than 1, 2, and 3. So we might have some type of like order delivery service or ordering service, maybe for number 1. Number 2, we may do like marketing effectiveness or something like that. Number 3, even though it's a two variable solution, they're very strongly related to tech support and warranty or something like that. And we probably name this 3rd one something along those lines. This 4th one, again, is a little quirky. It's hard to name this. If you can't name your factor, then it means you got problems. And you typically name your factor based on the components of the factor. So our product quality and our competitors and our competitive pricing, it's difficult to understand. We may need to go back to the survey to try to interpret this a little bit better. It may be that we're priced competitively, or maybe aggressively, or maybe our competitors' pricing. I'm really not sure how to interpret this very last one, so that's going to take a little bit more investigation. But basically what we've done is we've taken 13 variables and we've reduced them to 3 different components, or three different factors. So 1, 2, and 3, and so we've reduced our data, and now we're better able to explain these 3 latent variables that are not directly measured, but rather indirectly measured. And this is the initial approach in terms of how we choose our rotation method. And then we begin to interpret and modify the solution so that it makes sense for us, that we can move forward.